Hello all. We'll discuss about oxidation states in periodic properties. Atomic radius, ionic radius, ionization potential, electron gain enthalpy, electronegativity, electropositivity, valencies. Similarly, oxidation states are also one important point. This is to be discussed here under the periodic properties. So as we know, periodic properties means which are going to reappear after regular intervals. As they are going to appear after regular intervals, we'll see how the oxidation states are going to reappear. We know what is oxidation state. Oxidation state is the possible charge acquired by an atom in a compound. Possible charge acquired by an atom in a compound. It is a possible charge, not the exact state. Don't think that potassium permanganate manganese plus 7 means it is losing all the 7 electrons. Okay, now plus 7 means it is having 7 bonds in which it is having less electronegativity. If it is minus 2, it is having 2 bonds, and there it is having more electronegativity when you are discussing about the covalent bonds better. Now we'll go with oxidation states, how they are going to change in groups and periods. Any group if you take, generally oxidation state will be same. In general, I am saying in general, oxidation state is going to be same in general. But we'll take one by one group. Here we don't take any exceptions. We'll take one by one clearly. We don't want to skip anything. See, first year group elements. First year group elements, general electronic configuration is NS1. Means they are ready to lose their 1 electron. So plus 1 is the oxidation state here. Plus 1 oxidation state for NS1. Lithium plus, sodium plus, potassium plus, fixed beta. No other oxidation states are possible than plus 1 except hydrogen. Hydrogen is a non-metal, so you can expect your hydrogen plus 1 as well as minus 1. Okay, hydrogen minus 1 is possible when that is attached with metals. For example, sodium hydride is there. Hydrogen will show minus 1. Exception, you can take this as an exception, but all the exceptions also we'll discuss here now. So this is first point. Then we'll go to second year group elements. Second year group elements are beryllium, magnesium, calcium, strontium, all this. They are having an electronic configuration of NS2. Now you can guess what is the oxidation state for them. Yes, exactly. They are ready to lose their outermost 2 electrons. So even the covalent bond or anionic bond is formed, they are going to give 2 electrons, or they are less electronegative, more electropositive. So the oxidation state will be plus 2. Magnesium plus 2 only, beryllium plus 2 only, calcium plus 2 only, strontium plus 2 only. No other state we take. Magnesium plus we don't take beta. Magnesium plus 2 only. So for second year group elements, no exceptions. The common oxidation state is plus 2. For second year, plus 2 fixed. Now the interesting points will come. Third year group elements, if you see, NS2 NP1 is the common electronic configuration. Here I am taking boron, aluminium, gallium, indium and thallium. These are the 5 elements, important 5 elements. Sixth also we are taking not much known properties, no? So up to thallium only you consider. Here you see what happens in this case. NS2 NP1 is there. Because of this NP1, plus 1 oxidation state is possible. Extra, because of this NS2, more 2 oxidation states. That means 2 higher oxidation states are possible, not 1 by 1. Plus 1 and plus 3 are the possible oxidation states. First exception, boron being a non-metal. Boron, as it is non-metal, the oxidation state you can consider is even minus 3 also better. Like BH3 case, B2H6 case, you can expect minus 3 also. Otherwise plus 3 only, not plus 1. And of this plus 1 and plus 3 oxidation state, the most important point is of plus 1 and plus 3. Plus 1 down the group increases. Plus 3 down the group decreases. What is the meaning of this? The stability of plus 1 oxidation state down the group increases. Down the group plus 3 oxidation state decreases better. The meaning of that is aluminum can show plus 3 only, not plus 1. Thallium will show plus 1, not plus 3. Here one exception I will say. For aluminum case, plus 1 is never possible, but always plus 3 only. No other question. Aluminum is always plus 3 only. But thallium, it can show plus 1 as well as plus 3, both better. But generally it prefers plus 1. So what we want to mention here? So simple. Boron, aluminum, gallium, indium, thallium. Plus 3 oxidation state, if you are seeing, it is decreasing. That means aluminum is showing maximum tendency of plus 3, whereas plus 1 oxidation state stability increasing. That means last element shows more oxidation state in plus 1. That's why for thallium, plus 1 is more stable than plus 3. Tl, thallium chloride, TlCl3, it is not possible. TlCl is only possible. That means thallium is ready to show plus 1 oxidation state, not plus 3. Very simple logic. Why? Okay, now why is very interesting question here. See, when you see NS2NP1 configuration, good, boron, aluminum, gallium, indium, thallium, these are the elements we are discussing. We'll discuss in detail better because this effect is there for the coming two groups also. What we see is, this is period number I am writing. This is second period, third period, fourth period, fifth period, and sixth period. So thallium comes in sixth period. So when thallium is coming in sixth period, the electronic configuration of thallium, if you want to see, that will be like this. NS2NP1, when you are saying common oxidation state, that is correct better. But between this NS2 and NP1, that is 6S2 and 6P1, there are 4F and 5D orbitals also. This is the interesting point here. 4F and 5D. We know that 4F orbital screening effect is very poor. 4F, because of F orbital's poor shape, you say, not a proper shape. Because of its shape, it is not going to screen the electrons properly. Why? S orbital is spherical, nucleus is also spherical. So a spherical orbital can completely cover the spherical nucleus better. But F orbital is completely diffused. So this cannot screen properly. So F orbital screening is very less. 5D orbital, then 6P orbital. Okay, now after filling electrons into 6S orbital, then the electrons are entering into 4F orbital, 5D orbital. This is true. But the interesting point is, when you see the orbital, this is the nucleus beta, 1, 2, 3, 4, 5, 6. For example, let us say this is the sixth shell, this is the fifth shell, and this is the fourth shell. Maybe electrons are joining here. But 6s to 6p1 configuration is here only. That means 6s and 6p electrons are outside beta. Now, what happens here is, you see, this fourth and fifth shell, that is 4f orbitals and 5d orbitals, are not screening properly. When they are not screening properly, the nucleus power is increasing and attracting the 6s electrons inside. That will be more on the 6s electrons. So 6s electrons are not allowed to participate in bonding. This is called, the reluctance of participating in bonding is called inert pair effect. Inert pair effect is shown here in fourth group and fifth group beta, that is in last element. Thallium's outermost ns electron is not interested to take part in bonding. The reason is they are in more attraction of the nucleus. Reason is due to the lanthanide contraction. Reason is due to the poor shielding of f orbital. Reason is due to the shape of the f orbitals. Okay, due to the shape of the f orbitals, as they can't screen properly, the nucleus power is more on the outermost electrons and the ns electrons are attracted inside. So they are not going to participate. Only this electron is going to participate. This effect is called inert pair effect. Inert pair effect. In a single line, if you want to write the reluctance of ns electron pair to take part in bonding, is inert pair effect. This you can see in p block elements group 13, 14 and 15. The reluctance of ns electron pair to take part in bonding is called inert pair effect. Okay, so good. We'll go with another one. You see, group 14, ns2 np2. So common oxidation states you can easily expect now, you can easily guess now. Because of this p, because of this s extra 2, right? Top elements plus 4, bottom element plus 2 more stable. Got the logic? Carbon, silicon, germanium, tin and lead. Top element carbon, so plus 4 type of states, bottom element is lead, so plus 2 type of state. The reason is inert pair effect. Inert pair effect is the proper reason for this. ns2 np2, carbon silicon type of top elements will show plus 4 oxidation states, lead type of elements will show plus 2. We mentioned plus 2 plus 4 both are there beta, so germanium tin they can show plus 2 as well as plus 4, but generally coming down the group the lower oxidation state stability increases. Carbon can show even minus 4 also, but only for carbon. Silicon is of course non-metal, but not that much electronegative. See the next one, group 15. Group 15 elements are nitrogen, phosphorus, arsenic, antimony, bismuth. Electronic configuration is ns2np3. Now you can guess what is going to happen here. Plus 3 and plus 5 beta. Right. So bismuth, this is for top elements and this is for bottom elements as we know. So bismuth plus 3 more stable. Nitrogen, phosphorus type of elements can show plus 5 oxidation states. Okay, nitrogen is very special. We'll discuss about nitrogen. And nitrogen, phosphorus both are non-metals. That's why they can show even minus 3 also. Because by gaining 3 more electrons, they can complete their octet configuration. ns2np3, if you are adding 3 electrons extra, it will become ns2np6 beta. So because of this possibility, there is a chance of getting 3 electrons. So nitrogen, phosphorus can show even minus 3 also. And plus 5 is generally for top elements, and for bismuth that is going to be plus 3. Again, the reason we say is inert pair effect. So thallium plus 1, I'll just give you thallium plus 1 is more stable than plus 3. Remember these are very important points. Plus 2 more than plus 4, and bismuth plus 3 more than plus 5. Very, very important points you need to remember. The reason is inert pair effect. The reason is inert pair effect. Then the specialty of nitrogen I wanted to mention you. Nitrogen oxidation states you see NH3, N2H4, NH2OH, N3H, N2, N2O, NO, HNO2, NO2, HNO3. With these compounds you consider, the oxidation states are like this. Here it is minus 3, this is minus 2, this is minus 1, this is minus 1 by 3, this is 0, this is plus 1, plus 2, plus 3, plus 4 and plus 5. So nitrogen is an element which can show a wide range of oxidation states from -3 to +5, -3, -2, -1, 0, -1 by 3 also, +1 to +5. Okay. NH3 is ammonia, N2H4 is hydrazine, NH2H hydroxylamine, N3H hydrozoic acid, N2 is dinitrogen, N2O dinitrogen oxide, or you say laughing gas. Yeah, this is laughing gas, but N2O. NO is nitric oxide, HNO2 nitrous acid, NO2 nitrogen dioxide, HNO3 is nitric acid. This is the specialty of nitrogen. It can show wide variety. Okay, now here this is not periodic property. In general, as this point has come, I explained. Now we'll move on. Group 16, NS2NP4. Now you see only 2 electrons are required to get the stability. So -2 is also possible. Otherwise this +4. Otherwise this 2 +6. Interesting thing is NP4 means there are 2 unpaired electrons. Because of these 2 unpaired electrons, they can show -2. Because of these 2 minus, they can show even +2 also better. So this we explain in terms of this, you see. NS2, NP4 is the configuration. 1, 2, 1, 2, 3, and 4. Number of unpaired electrons you have to check. This is called ground state electronic configuration. In ground state electronic configuration, number of unpaired electrons are 2. So it can show +2 or -2. Now I am going to make this excite. Excite means electron is going to jump from lower orbital to higher orbital. Their ND orbital will be there, that is with 0 electrons. So when electrons are jumping from lower orbital to higher orbital, you check here, d orbitals, 5d orbitals will be there. One of the electron is jumping from this place to here. Now number of unpaired electrons are going to be 1, 2, 3, 4. So in excited state, only positive state it shows, not negative shows, because this excitation takes place only in the presence of more electronegative elements. That's why they can show plus states. Similarly, one more electron pair is there that can also jump from here to here. So in that case, the electronic configuration will be s orbital with 1 electron, p orbitals with 3 electrons, and d orbitals with 2 electrons. Total number of unpaired electrons are going to be 6. Okay, so -2 possible, +2 possible, +4 possible, and +6 also possible. This is called ground state electronic configuration. When first electron jumped, it is called first excited state, and when second electron jumped, it is called the second excited state. First excited state +4, second excited state +6, ground state -2 and +2. This type of discussion not required till group 15, so I didn't explain. From here it is required, but we'll take the same in group 17 also. See group 17. Group 17, NS2, NP5 beta and ND0. So NP5 means it will be like this. One unpaired electron is there. Because of this one unpaired electron, it can show -1 +1. This is called ground state. Now d orbitals also I am showing here. See 1, 2, 1, 2, 1, 1, and 1. Number of unpaired electrons 1, 2, and 3. So it will show +3, and this is called first excited state. Similarly, you can make this electron pair jump here. Now in that case, there will be 5 unpaired electrons. 1, 2, 3, 4, 5. Already 3 are there plus extra 2. So this is +5 second excited state. In the same way, when it is also jumping, total 7 unpaired electrons will be there. So +7 is also possible. -1 +1 in the ground state, +3 in the first excited state, +5 in the second excited state, +3, 7 in the third excited state. -1 +1 +3. But here again exception is fluorine. It shows only -1. The reason is high electronegativity. Because of high electronegativity, it shows only -1 oxidation state. Only -1. Okay, now F2 is 0. But in all the compounds, fluorine is going to be -1. Then coming to noble gases better. Noble gases oxidation states are 0. Noble gases oxidation states are going to be 0 because no bonding, nothing discussion. Now the interesting part, D block elements. They show variable oxidation states, means more than one oxidation state is possible. More than one oxidation state, variable oxidation states. You see, the lower oxidation state is equal to number of s electrons. The higher oxidation state is equal to number of s electrons plus number of unpaired d electrons. I will explain one by one all the 3D series elements, don't worry. Lower oxidation state is equals to number of s electrons. Higher oxidation state is equals to number of s electrons plus number of unpaired d electrons. See, let's start with scandium. Scandium is 4s2 3d1. Scandium is exception. Don't expect here this as well as this all. Scandium shows only +3. This is like exception. You can expect this question IIT NEET type of exams. Scandium oxidation state only +3. Only +3. No exception. No other things. This is pure exception. Titanium, if you see, 4s2 3d2. So what I told you, the minimum oxidation state is equals to +2. And d orbital d2 configuration means it is like this better. So if you want to see, +2 is the lowest, and one by one you add this +3 and +4 one by one, because they can show variable oxidation states better. So +2 to +4, all oxidation states are possible. Vanadium, if you see, 4s2 3d3, 4s2, it's a pair, 3d3, 3 unpaired electrons. Just now we were discussing the minimum state, number of s electrons, the maximum state, one by one you add. So the oxidation state up to +5 is possible. You know about vanadium pentoxide V2O5. Oxidation state of vanadium is going to be +5. Example I am saying. See one more. This is interesting. Chromium 4s1 3d5. The minimum is +1, and d5 means there are 5 unpaired electrons. 1, 2, 3, 4, 5. So +2, +3, +4, +5, +6. One by one we are adding. So the oxidation state highest for chromium is +6. Lowest is +1 beta. Lowest is +1. So till now we got the lowest is for chromium only. The rest were showing from +2. Scandium is only +3. Manganese. Manganese is 4s2 3d5. 4s2 means +2. d5 as I told you just now. +3, +4, +5, +6, +7. So manganese is the highest in 3D series. In the 3D series, the maximum oxidation state is for the manganese. +2 to +7. KMnO4 is the best known example to you. Manganese. Now the twist comes, you see. Iron. 4s2 3d6. 4s2 means it's a pair of electrons. As we were discussing, minimum is s electrons. Done. 3d6 means 1, 2, 3, 4, 5, 6. I told you not to take this one. This is a pair. We need only unpaired electrons, but only 4 are there. So add 4 more, plus 3, plus 4, plus 5, and plus 6. Maximum oxidation state for iron is going to be plus 6. Highest possible is plus 6. Cobalt 4s2 3d7. Nickel 4s2 3d8. All these you can apply in the same way beta. The problem comes with 4s1 3d10. 3d10 means completely filled. 4s1 means it should be plus 1 beta. But interestingly, copper again exception, it shows even plus 2. And very interesting thing is it is more stable in plus 2 only. It is more stable in the plus 2 oxidation state only. So copper plus 1 plus 2 and zinc is 4s2 3d10. So it is plus 2. In one line, if you want to show scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. These are the 3D series. This is only plus 3. This is plus 2, plus 3, plus 4. This is plus 2, plus 3, plus 4, plus 5. It is plus 1. Okay, to plus 6. This is plus 2 to plus 7. This is plus 2 to plus 6. This is plus 2 to plus 5. Plus 2 to plus 4. Copper plus 1 plus 2 special, and zinc is only plus 2. So it increases like this and decreases. So highest is given for manganese with a plus 7 oxidation state. And other important highest states are osmium tetroxide and ruthenium tetroxide. And even you can take xenon tetroxide also. Here the maximum oxidation state of plus 8 is seen. The highest oxidation state ever known is plus 8. That is shown by osmium, ruthenium and xenon in their oxides, plus 8. So this is about D block elements, and remember D block elements general electronic configuration is ns1 to 2, n minus 1d 1 to 10, and common oxidation state is plus 2. Even though scandium won't show, but in general D block general oxidation state, if anyone is asking, that is plus 2. For F block it is plus 3. F block there is no need to discuss much in this way, but remember simply plus 3 is possible. Okay, F block elements common oxidation state is plus 3. D block elements common oxidation state is plus 2. Zero group elements 0. Alkali metals plus 1. Fluorine is always minus 1. Generally oxygen minus 2 except to fluorides. Some peroxides and all are there that we will discuss in stoichiometry topic. So hope you enjoyed this session. Signing off, Lakshma Reddy. Will meet you with a few more lines are there to complete this lesson, that I will try to give you as soon as possible. Done. If you have any doubts, you can message me on my number, or you can mail me on my ID. Done. Have a wonderful time. Good day.